Look at this terminal on the left. A standard extraction script is running, returning a continuous stream of HTTP 200 OK statuses. But look at the database table on the right. It's ingesting blank strings, null values, and UI artifacts like submit or loading. Traditional scrapers operate as optimistic machines. They are built on the fragile assumption that dynamic web applications are static documents that load the same way every single time. The modern internet operates non-deterministically. Websites hydrate dynamically, load content through asynchronous GraphQL calls, run A/B layout tests, and silently mutate their DOM structure whenever a front-end engineer refactors a component. When mutations occur, extraction scripts rarely crash. They don't throw a loud stack tracing panic that engineers can easily catch and debug. Instead, the system experiences a silent failure. The script simply keeps running, blindly executing obsolete DOM selectors against a mutated layout. The consequence flows downstream into the data architecture. Analytics dashboards and machine learning models ingest this completely corrupted text, manufacturing false confidence at scale. The industry's default response is an arms race, throwing proxy rotators, remote headless browsers, and opaque infrastructure at the target. But attempting to spoof human behavior only masks the underlying fragility of the script. Reliable extraction requires abandoning VIDES-based DOM parsing. To extract accurately, we must treat web scraping as a strict, typed contract enforced by runtime assertions. Data pipelines are only as strong as their upstream validation. Tolerating silent corruption at the extraction layer invalidates the entire engineering effort downstream. The primary barrier to programmatic extraction is access. Modern bot mitigation, CAPTCHAs, and complex authentication flows actively prevent automated scripts from reaching the data. Replicating complex browser states on remote servers is easily detected, yet we naturally bypass these hurdles every day when operating a local desktop machine. This architectural diagram shows a different approach, decoupling discovery from execution. We split the pipeline into two distinct stages, human-guided discovery and headless extraction, bridged by a distinct handover. In stage 1, a human operator uses a highly visible local browser to organically navigate the target site. Because it is a real, local browser, the operator can manually clear cookie consent banners, solve the CAPTCHA, and establish an active, stable session. The human organically solves the access problem. The first critical output is session.json, capturing the exact cookies, user agent, and authentication state. The second output is intent.json, a declarative recipe of semantic hints, selectors, and pagination logic chosen visually. Decoupling allows human intuition to solve the complex, unscriptable access problem exactly once, allowing the machine to safely take over the infinite repetition. In a rigorous data pipeline, intent.json cannot operate as a loose list of selectors. It must function as an executable agreement. This JSON snippet is the golden seal, the definitive structural fingerprint of the web page. The row count establishes the exact number of expected items on a paginated list. The field population metric measures layout behavior. 1.0 means the title always populated, while 0.95 means the price was occasionally absent. Traditional scrapers rely on simple conditional logic. If a field exists, grab it. The golden seal replaces that ambiguity with strict percentage-based fingerprinting. This establishes a baseline reality. It tells the headless engine exactly what the web page is supposed to look like under normal operating conditions. When we transition to stage 2, the headless execution engine boots up, importing both the session.json auth state and this newly minted golden seal. This contract acts as the ultimate source of truth, transforming the chaotic web DOM into a rigidly typed structure against which errors can be actively measured. The automated extraction pipeline begins. The headless engine stealthily navigates the target, using the organic auth session to move undetected. This flowchart details the defensive layer, shift-left QA. Raw data attempting to reach the final database is intercepted by an in-memory gate holding exactly 5 rows. Corrupt data must be intercepted before it is ever written to disk. Inside this QA buffer, raw rows must run a gauntlet. They are subjected to semantic validations, constantly measured against the baseline established by the golden seal. The first validation check is the density invariant, which measures runtime layout stability. If the golden seal expects 20 rows and the runtime extraction yields 3, the density invariant fails. It instantly detects if a page is unhydrated or overhauled. The pipeline resets. The lineage invariant then measures selector drift, comparing an expected 1.0 title fill rate against a reality of just 10%. A lineage invariant failure proves that a specific DOM element has mutated. Even if the total row count remained identical, the individual selectors are no longer pulling the correct data. When an invariant is tripped, the system does not bypass the error to write empty columns. The circuit breaker engages, severing the execution flow completely. 0 bytes of garbage data are permitted to exit the QA buffer into the downstream pipeline. Halting the entire pipeline at the point of ingestion is exponentially cheaper and safer than allowing corrupted data to pollute a data warehouse. The most dangerous characteristic of a scraper is not a high failure rate, but the lack of an audit trail when a failure occurs. This terminal shows how the system alerts programmatic supervisors using strict semantic exit codes, like code 3 for structural drift or code 42 for auth required. Upon a tripped invariant, it generates a forensic bundle. The crucial file is failure_snapshot.html, an exact redacted visual record. This snapshot captures the exact state of the DOM at the millisecond the machine recognized an alien landscape, whether it encountered a new Cloudflare challenge or an expired login redirect. This diagnostic evidence eliminates the guesswork. Developers no longer have to blindly write custom scripts to reproduce the remote environment. This observable rigor stands in stark contrast to black box AI scrapers that promise magic, but silently hallucinate CSS paths, leaving engineers with undebuggable errors. The web will keep changing. Front-end engineers will keep refactoring components, and selectors will inevitably break. The ultimate goal of a data architecture is not to build a scraper that never breaks. The goal is to build a deterministic system that refuses to lie to its engineers.